Thank you. Hi, everyone. Today I'm going to talk about constructions of locally testable multiplication codes from high-dimensional expanders and like objects. This is based on joint work with Irit Dinur, Rachel Zhang, and Hui Pham. Okay, so I know that in the past couple of days, you probably have heard a lot about codes and high-dimensional expanders and tenor codes and stuff. So I will quickly go through the preliminaries so that we have common notation for talks for things that we'll be talking about later in the talk. So let's just say we'll be considering codes in this talk, and more specifically, we'll be only considering linear codes of some finite vector space Fn. And I'll use the notation K to denote the dimension of the subspace, and also use little r and delta to denote the rate and the relative distance of the code. And really quickly, let's review the definition of tenor codes. So specifically, I'll be looking only at bipartite graphs. So given a bipartite graph G with vertex set L and R, and also it's a right regular bipartite graph with right degree dr, and also given a local code C0 with block length dr, then we can define this tenor code for this bipartite graph G and this local code C0 to be the set of code whose coordinates essentially correspond to vertices in the vertex set L, and also who need to satisfy the following conditions. So for every vertex V from the right side, we want that the code word restricted to the neighbors of V. So the notation being C restricted to V, this local view should belong to this local code C0. So that is the condition. Two comments that we'll make for these tenor codes. So one is that we will be able to obtain bounds on the dimension of this tenor code in a black box way if we have good enough rate R0 for this local code C0. So in particular, if R0 is big enough, where the threshold is determined by a number which depends on the left degree of the vertex, left degree of this bipartite graph. So also I want to comment that both the left degree and the right degree, we should treat them as just constant in this talk. So these are just constant that doesn't depend on the size of the vertex set L or R. So if the local code C0 has good enough rate, then we'll be able to obtain a dimension lower bound for the bigger tenor code, which is actually linear in the block lengths. And another comment is that if the second eigenvalue of this bipartite graph is small enough, it's smaller than the relative rate of this code C0, then we'll be able to get a constant lower bound on the relative distance of this code. So this is simply black box. We don't need to dig too much into the structure of the graph and the structure of the C0s. Okay, so next we'll recall the definition of locally testable codes. So we say that a code C is alpha locally testable if there exists a constant query randomized tester T, such that when it's given any vector X, the Hamming distance from X to the code space is upper bounded by some constant times the rejection probability of this tester when given the oracle X. So an alternative way of saying this is that if the rejection probability is small, then X must be close to the code space. So in general, there's no fixed way of showing a given code is locally testable. However, if we happen to know that this code C is a tenor code, then there are some standard approach that one can try to prove that C is locally testable. In particular, if C is a tenor code with local code C0, then we can consider constructing a candidate tester T that make use of the local tester T0 for this local code C0, which supposedly should test whether should be a local tester for the global tenor code C. So we'll construct this natural candidate tester T in the following way. What it does is it first samples a random vector V, a random vertex V from the right-hand side of this bipartite graph. And then it look at the restriction of this input string X to the coordinates that are neighborhood of this V, and then use the local tester T0 to check if this X restricted to the neighbors of V is inside the code C0. Okay, so we have this tester T. Now we're going to talk about really what is the sufficient condition for the tenor code C to be locally testable with this tester T that we just constructed. So the first condition is, of course, something we already mentioned, which is that we're actually making use of this T0, which actually help to locally test the local code C0. But another very important property is that we need the bipartite graph G together with this local code C0 to have the so-called agreement testable property. So you probably have heard already maybe in the last week about agreement test, but I will reiterate here in the language that will be more, will align better with the proofs I will use later. So let's recall. This agreement testable property is essentially just saying that given a set of local code words CV, one for each V that's a vertex inside R. So we know that these local code words, they would have shared coordinates because vertices in R have shared neighbors in the bipartite graph. So if most pairs of local code words with intersections actually agree on their intersecting coordinates, then we have that there actually exists a code word C inside the tenor code, so that most of these CVs from this collection agrees with C's restriction to the neighbors of V. So let me try to be a little bit more precise here. So this property is asking for the following. They're asking for a distribution mu over pairs of vertices from the right-hand side of this graph G, such that these pairs should have intersecting neighborhood. And what the property is asking is that under this distribution, with very high probability, the corresponding local code words CV1, CV2, if they agree on their intersection, then they're very close to some global code word C inside the tenor code. An alternative way of saying it is that if the probability under this distribution mu that CV1, CV2 disagree with each other, if this probability is small, then actually most of the CVs would agree with restrictions of the global code C. Okay, so that's why it's called agreement testable. It's about bounding disagreement. Okay, so these are the two sufficient conditions to prove that the tenor code is locally testable. The proof actually isn't too complicated, so we'll next give a proof sketch. This proof kind of underlies many of the results we'll be mentioning and talking about later. So let's actually look at how this proof goes. Okay, so essentially what we're trying to do is we're trying to prove that this code C is actually locally testable. So in order to do that, we need to connect the distance from X to the code space and upper bound it with the probability of rejection using the tester T, right? That's what we want. So in order to do that, what we do is for any given string X, we first define little c to be the closest code word in the tenor code to the string X. Furthermore, we also define a collection of local code words CV such that CV is the closest code word to the restriction of the string X to the neighbors of V. So we have a closest code word and also a bunch of like local correction in some sense. Okay, now with the help of these collection, we can upper bound the distance from X to the code space with the following two average distance. The first one is the average distance from the restriction of X to V to the local correction CV. And another average distance is from these local correction CV to the restrictions of C to the local neighborhood of V. So this is just triangle inequality. And next, we're going to just bound each distance separately and try to relate them to the rejection probability of T. Okay, so we note that actually, if we look more closely, this is precisely the distance from some string to really the local code C0. Because we know that by condition 1, our C0 is really a locally testable code with tester T0. So by definition, this distance can be upper bounded by the probability that this tester T0 will reject this restriction of X to V. That's just using condition 1 directly. Of course, there's a constant, but let's not worry too much about it. But notice that we're actually taking an average over all the different choices of V here, all the different choices of restriction here. But note that actually, if we take an average over all such probability, that quantity precisely becomes the probability that this tester T would reject this string X. This is by construction of our T. So we see that in 2 steps, we already connect this average distance, local distance, to the probability that this tester T rejects. So we're halfway there. Next, we're going to prove that the second distance here could also be related to the rejection probability. Okay, so how we're going to do that is the following. So we first know that the average distance from CV to the restriction of C to V can be upper bounded by the probability that this local code word CV disagree with the restriction of C to V, right? Because distance is always a number between 0 and 1. And here, using this probability, we're just putting anything that's non-zero to 1. So it's an upper bound. And now this looks like familiar because this is a quantity that actually appear in our condition when we appear in our condition of agreement testable property, right? So by agreement testable property of the tenor graph and the local code C0, we can upper bound this probability, this distance. In some senses, this is another way of measuring distance from the collection of CB to the global code space, the tenor code. So we can upper bound this distance with this rejection this disagreement probability. So it's a probability that when we sample a pair V1 and V2, the corresponding local codes disagree on their intersection. Okay. So whenever this happens, whenever we have a pair CVs and CV1 and CV2 that disagree on their intersection, what we know is that in their intersection, either CV1 or CV2 would disagree with the original string we start with, which is X. Because if they both agree, then they should totally agree on their intersection, right? So in this way, we can actually relate this disagreement probability with the distance from X to each individual CVs. Don't worry too much about the intermediate steps, but the gist is just that this disagreement probability can be somehow upper bounded by the expected distance from the restriction of X to V to the local correction C sub V. So now we know that this expression is precisely the first term in the sum that we had here. It's just distance from the restriction to its correction. And we know from the calculation before that this can be upper bounded. This average distance can be upper bounded by some constant times the rejection probability. So again, we're able to upper bound the second term also with some constant times the probability that the tester rejects X. So, okay, so now we have both steps, and putting them together, we directly get an upper bound of distance from X to the code space in terms of the rejection probability of the tester T. So that's just the end of the proof. Okay. So now that we know a way of proving that tenor codes are locally testable codes, what do we know about the currently best known locally testable codes? So it turns out that the currently best known locally testable codes are actually coming from these tenor code construction. In particular, these are the codes due to Dinur, Evra, Levny, Lubotsky, and Moses. And what they do is they use the so-called left-right Cayley complexes, which I guess you already heard about in David's talk and others' talk yesterday. The construction of this Cayley complex. And with from this complex, we can actually construct a tenor code diagram, just similar to the way we drew it before. So specifically in this left-right Cayley complex, it's a square complex. So it consists of vertices and edges and faces, which are squares. And I can draw this diagram over here where the blue squares are really just correspond to squares in this complex. And the blue dots are edges and the pink triangles are vertices. And these edges indicates containment relation between these sets in the adjacent layers. And we can define from them a tenor code by really treating these squares as the set L in our notation, which correspond to the coordinates in our code space, in our code. And the edges correspond to the local test T. And also the vertices correspond to the restrictions that we take when we consider like local codes. So in this construction, what they do is they actually use the tenor code structure. They use this graph as the G, and then they find proper choices of C0 so that they can actually get constant rate and constant relative distance. Both of these are obtained in the black box way that we talked about at the beginning. So they're able to choose a local code that have pretty good rate, and also they're able to construct such a left-right Cayley complex with really good expansion property. Okay, and it's optimal, it's asymptotically optimal simply because like a constant rate and constant relative distance is the best we could hope for. Yeah, so this is the locally testable code construction that we know about. Next, I'm going to talk about a more specialized class of locally testable codes, which are locally testable multiplication codes. I believe in David's talk yesterday, this notion is already brought up. Here, I will just briefly motivate it from the program checking perspective. So let's consider a specific example. Like in program checking, basically, we would like to check relations on encoded data efficiently. And here's an example of where it would come up. So one pretty commonly checked type of relation in these kind of setting is that we would be given three vectors, M1, M2, and M3. And we'll be asked to check that M1 entry-wise product with M2 is equal to M3. This type of relations comes up when you want to do checks on like all kinds of algebraic circuits and R1CS problems and stuff like that. So if one want to do it with few queries, what should we do? First thing to note is that checking equality with field queries is already something we know how to do. What we could do is we just use locally testable codes and encode the vectors on the two sides of the equations with locally testable codes. And then what we need to do is just first check that these two vectors are close to valid code words. And then after we make sure that's the case, what we can do is then we just sample random coordinates in this in the code, and then check whether the two vectors agree on those coordinates. So checking equality we could already do, but that's not quite sufficient because we would additionally also need to check that a given vector x is indeed the encoding of the entry-wise product of two vectors. So one natural way of doing that is to make use of the locally testable multiplication codes, C and C prime. So C and C prime would have the following property. If I encode M1 and M2 under the code C, respectively, and then take the entry-wise product of their encoding, the vector I get is actually equal to the encoding of M1 entry-wise product with M2 under the code C prime. So once we have such property, what we can do to check this original equality over here is we can simply just encode M1 and M2 using the code C and encoding M3 using the code C prime. And afterwards, we sample random coordinates in the vector and check that this relation hold for each of those individual coordinates. Okay, so that's the kind of a simple example in showing that what potential applications one could have for locally testable multiplication codes, but also more deeply, I guess it's related to like all kinds of proof systems, including like PCPs and also even the more interactive ones. Okay. So we actually already know examples of locally testable multiplication codes. It turns out that Reed-Muller codes are actually locally testable codes with multiplication property. Let's just quickly recall like a Reed-Muller code is just the evaluation of some low degree function on n variables. So here the notation n is number of variables in the function and d is the degree bound and p is just the order of the field that we're considering. So first, Reed-Muller codes are locally testable because we can do the following local test. Inside this vector space that we evaluate this function, pick a random affine line, and then check that this evaluation restricted to the affine to this line actually is a degree at most d function. So that's the simple local test. And furthermore, Reed-Muller codes are also multiplication codes because let's consider two code words, which are evaluations of function f1 and f2, both of degree at most d. So if I take the entry-wise product of their encoding, I end up getting a evaluation of a function that's of degree at most 2d. So we know that code word comes from the code space of Reed-Muller codes, n variables with 2d being the degree bound. So in some sense, saying Reed-Muller with nd parameter and Reed-Muller with n2d parameter have this multiplication code property. So this sounds good. However, we run into the problem that this Reed-Muller code's dimension or its rate is not good. In particular, we are interested in a case that P is a constant, so we're looking at a finite field. And because of that, the degree D also is a constant. So in this case, the block length would be P to the N, number of points we evaluated at, and the dimension is essentially N to the D. So it's polynomial in N, but the block length is exponential in N. So the rate is really sub-exponent. It's really inverse exponential rate. So it's not very good.
Siqi, about 5 minutes.
Yeah. Okay. 5 minutes. Okay, so the big question here is whether we can improve this rate. Okay, maybe you would think that, okay, one way of doing that is just to make modifications to the already known good constructions of locally testable codes. So that would be good, except for although doing so by replacing the local codes with removal codes, that would actually give you like locally testable codes with multiplication property. However, the big problem there is that we no longer get constant rate, because to ensure that removal codes are locally testable, what we would end up needing to do is to make its rate not too high. But if we do that, we can no longer use the black box way mentioned before to prove lower bounds on the rate. So in that sense, it doesn't quite work. But there's some alternative way. So in this joint work with Dinur and Zhang, what we did is we improved the rate of removal code by actually using high-dimensional expanders to construct punctured removal codes. So we remove some of the evaluation points. And the improvement we get is the following. So if we insist on the dimension still being n to the d, we can give polynomial improvement on the block length. So now the block length is p to the n to the 8/9. So still not too big of improvement. And this construction is actually based on a Tanner code over this Kaufman-Oppenheim two-dimensional expanders. So what we do is we also didn't use any black box way of proving it. We actually open up this construction and realize that there is a natural way. In this construction, we still just have vertex. It's a two-dimensional simplicial complex. So we have vertices, edges, and triangles. So it turns out that there's a natural way of viewing all these triangles as vectors from some vector field fp to the n. And also the edges as the edge, basically given an edge, if we look at all the triangles that this edge participates in, they form a affine line over the set of points that we picked. Furthermore, like if we look at each vertex, the set of triangles it participate in actually form a three-dimensional subspace in this vector space. Because of that, it naturally gives us a way of puncturing rate-Muller code. Essentially, we just evaluate the rate-Muller code over the subset of vectors specified by this construction. And we do test on the lines. It's simply like that. Okay, so this is this construction. It turns out that we could even get further improvement. This is a bigger improvement here. So this is still this new result by doing work with FEM. We also still puncture rate-Muller code, and if we keep the dimension to be n to the d, the block length now is like 2 to the n to the epsilon for any constant epsilon. So it's a much better improvement on the rate, but still it's like it's not inverse polynomial rate. So a lot to be desired still. And this construction comes from the so-called Grassmann expanders. So these Grassmann expanders, they're not simplicial complex anymore. These are partially ordered sets where the base elements are simply points from a vector space, and the higher dimensional face correspond to subspaces in this vector space. So in the construction, we're considering where if I insist on like having dimension be n to the d, I would look at a construction where the top dimension faces in this Grassmann need to have dimension d cube. And these we're looking at a specific construction of this Grassmann expanders due to Golowich and further improved by in a joint work with Dickstein and Wigderson. This allows us to actually remove lots of points, and we're to the point that we're just left with 2 to the order, like exponentially and n to the epsilon number of points. But still, we are able to ensure that there are enough number of subspaces that's spanned by points in this space. Okay, so I guess, okay, I have no time, so I will not talk about this, but just 2 last sentence, which is like the open questions. So one open question is to improve the rate of locally testable multiplication codes. So far, we see that it's still very far from just even inverse polynomials. So could we do that? Another thing I think is more concrete and also very worth trying is, can we prove lower bound for on the rate of locally testable codes in which we just take the Tanner code construction from one of these very good locally testable code with linear dimension, and then replace its local code with some code with multiplication property, for example, remoter code and multiplicity code. We can no longer prove a lower bound on their rate using black box method, but could we look into the constructions and prove any non-trivial lower bounds on their rate? Okay, that's it. Thank you.
Can you hear me?
Yeah.
Okay. So you mentioned these punctured Reed-Muller codes somewhere in the construction. So retrospectively, the point sets, the points of evaluation there, are they somehow natural with respect to working with low degree polynomials, or is this something that comes out of the HDX construction underlying the proof? I'm not sure how concrete the question is, but.
I see. I think I feel I understand to some extent. Like I would say the first construction from the Kaufman-Oppenheim coset complex, that one is, I wouldn't say is that natural. That one comes more from the underlying high-dimensional expanders construction. So, but I would say the second one, the underlying valuation points are pretty natural. And actually, there's some like not too difficult way of describing those points. Essentially, these are vectors, which if you reshape it as matrices, they're matrices of a certain rank. So I feel that's a relatively natural thing to think about. Yeah.
Yeah, are there any barriers for further improvement using HDXs?
It's a good question. I'm more hopeful about Grassmann expanders, but those things are harder to construct. So yeah, I would say I'm not sure. I don't see a very direct, like a very, yeah, I don't see anything immediate.
Can you hear me now?
Yeah.
So this is regarding the lower bound on the local rate R naught in the Tanner code. So, because that just came from pure dimension counting.
Yeah.
But when it's a locally testable code, one does believe there are a lot more redundancies. So do we expect that this is actually the lower bound, or can actually, this is just the, are there examples for which do we know that this is tight?
I see.
Even for the C cube LTC construction, this is how the lower bound is, the rate is discussed. We know that this is the rate of the code, or the rate is actually significantly, you can have rates with even smaller R naughts, codes with.
Yeah, I see. I'm not sure, but I feel especially in the short answer is that I don't know. And I feel it's unclear. It's very unclear, especially in the setting where the black box way doesn't work. I think if it's in the setting it works, maybe it is, but I'm not sure. Yeah. But I think it's very worth studying, especially in the setting where we actually replace it with something concrete like remolar codes.
Thank you.
Thanks a lot, Siqi, for the talk, especially at this late hour. Thank you very much.